Yeah.
No, second lecture of Hope. There was one lecture and one tutorial. Now this is the second lecture. Over to you, Hope, now.
Okay. So last time we state our problem, right? So we want to study the conversion of this function, the so-called, we can call it the symbolic depth function. So we have a polynomial ring R, and we focus on a monomial idea I. And usually I will just take I to be unmixed. This is a more interesting case. And then we take the symbolic power of I, and we want to know whether if we take the depth of this, then whether this limit exists or not. And actually, there is there are some known results related to this. So, for example, in general, we know that if I is any monomial idea, then by using results about the finite generation of the symbolic rings algebra. Yeah? This is a symbolic rings algebra, and SOKB and Chung proves that this guy is not real. If I is a monomial idea. And then from this, you can deduce that this symbolic depth function. Yeah? This I call the symbolic depth function of I. And this is eventually periodic.
But this case is different from the one you already explained, result of Professor Chong, the limiting case.
Yeah, so this is in general
Where the number of bipartite components one.
The one about
the number of bipartite components.
Yeah, that is for SID and for ordinary powers. Yeah? And this is for symbolic.
For ordinary power. Oh, okay.
Yes. And okay, and if more of I is square free, monomial idea, then actually this symbolic depth function is conversion. Yeah? And it is due to Hua, Kimura, Serai, and Chenamchu. So actually what we will do today is that we show that in general this limit need not exist, so it can, the symbolic depth function can be really periodic. Yeah? And what is the easiest example? So you can easily show that if the depth function, symbolic depth function is 0 at some point, yeah, then it would be always 0. Yeah? If I is unmixed. And yes, and this depth is 0 for some t's, and this can only happen if I is m primary. Yeah? So the dimension of I R mod I is already 0, and so this and this is equivalent to the depth. The symbolic depth function is identically 0, and so the case that we should consider is the depth symbolic depth function with value at least 1, right? So positive depth symbolic depth function. This is the first interesting case, and if you want to be this symbolic depth function to be eventually periodic, then at least you should have some value, at least 2 somewhere, right? If it is only 1, then it is, of course, it is convergent. So this will be what we are interested in. So when can you say that's a
Excuse me, Hope, can you go a little bit upstairs, upside? Yeah, redundant. So, so regarding to the restring, the result of Herzog, Hibby, and Chung, this is regarding to the restring, or this is regarding to R when you are defining the symbolic depth?
the symbolic restring is called the symbolic restring. R is always a polynomial ring, and it is always Noetherian.
Yeah.
Okay.
So the result is for okay. The definition of symbolic depth function is for RS or is for R.
It is simply this function, the function mapping T to the depth of R modulo I to the T symbolic power. That is called the symbolic depth function. So it maps some positive integer to some.
So what is the role of symbolic Rees algebra?
The symbolic Rees algebra is this ring. Yeah? It is a ring. And the symbolic depth function is a numerical function. Yeah?
So this is only depth of R over I symbolic T, or just I was just want to confirm, or RS quotient with IT.
Okay, so I mean, we are looking at this function here, mapping some positive number to the depth of the T symbolic power of I. And this is called the symbolic depth function of I. It is a numerical function.
Okay, thank you. You just gave the definition of symbolic Rees algebra just for the defining. Yeah, okay.
So this result tells you that this symbolic depth function is eventually periodic.
So, I was just okay. Thank you.
So yes, so in order to find a really periodic depth function, then we are interested in the question: when is the depth of some symbolic power at least 2, right? And that is what we are doing now. So we will discuss in general combinatorial.
Excuse me, Professor, I have a question.
Yes.
So you said this symbolic depth function is periodic, right? So
eventually periodic for a monomial idea. Yeah.
Okay, so can you like give us a comment on what has caused periodicity in this function? I mean, just maybe.
Yeah, it comes from the Noetherianity of the symbolic Rees algebra. So it is more or less similar to the case of ordinary power. In the case of ordinary power, you have okay, just 1 minute. In the case of the ordinary power, yeah, you have the Rees algebra. So just take the usual power, and from this ring, it is the Rees algebra. And in the case of symbolic power, you have the symbolic rings and zebra, very similar, but the regular components are given by the symbolic power. Yeah. So that they are they look similar, but they are very different. So this guy is always Notarian and standard weighted. Notarian and standard weighted, meaning that it is generated in degree 1 over R. But this guy is in general neither Notarian and nor standard weighted. So it can, you may need a generator of a different degree 1, 2, and so on. So in the case of monomial idea, yeah, then you have notarianity. And so so this give you this give you the outcome that the symbolic depth function is eventually periodic. Basically, the same argument. So you use that because the Rees algebra is Notarian, the depth function is always eventually periodic. But but here we have the standard graded condition, and the standard graded condition tells you that it is not only eventually periodic, but periodic of period 1, and of course periodic of period 1, meaning that it is eventually constant, right? But here the period can be larger than 1, and that's why we have periodicity.
And what is usually the relation between the depth of RIT and the symbolic power of T, which is greater or less in general?
This one and this one.
Yeah.
Is
there any relation between these two? Inequality or?
Yeah, in general, no relation.
In general, no relation. Was it studied before or not? For particular classes of ideals?
Yeah, I mean, usually they people do not compare between the depth of ordinary and symbolic powers. Yeah, I don't know.
Yeah.
What is that?
They are completely independent, so incomparable.
There is some relation, but yes, it's difficult to tell. Okay, so
sorry, I didn't get the answer. What did you say? I'm sorry.
So there's, I would say there is no relation in general. You have, you can try, give it a try. Yeah, it is.
Yeah. Okay.
It is a good question. Yes.
Thank you.
So coming back to our lecture today, we will give a combinatorial condition, ensuring that in terms of the degree complex, for an unmixed monomial idea. Such that it has depth at least 2. Okay, so but for that we will give condition in terms of the degree complexity. Recall from last time that for this you have the notion of the negative support. Yeah? A here is a vector in RD, right? And in Z to D, sorry. And so the faces of this form, yeah, F subtract to GA, where F is a subset of D containing GA, such that x to the power A is not contained in I localized at F. And last time I tell you that it is very easy to prove that. So for A equal to 0, I denote delta A by delta I. Yeah? So this is by definition delta of 0 of I, where A is the 0 vector. And in this case, you can so that this is the radical of I is exactly the standard rational idea of this guy. Yeah? So this is for F containing D such as a product of everything you have is not contained in the radical of I. The radical of I is a square free idea. And so this you can check. This is the standard rational idea of delta of I. Yeah? And moreover, you can prove also easily that for A in Z to the D, and if you have that F minus G of A is a phase of delta I, then F actually is a phase of delta I without A. So now our goal now is to describe completely this complex when I is unmixed. Yeah? And for that we will describe the facet of this complex when I is unmixed. So maybe it is useful to recall a few things and do a few relevant things first. So first we remark this is not so difficult, but it is useful to recall this. If delta is simply so complex, then you can compute the -1 reduced simply so homology, and this guy will be 0 if and only if delta is not this complex, the complex with only one phase, which is the empty set, and the degree zero homology is vanished if and only if delta is connected. Yeah? So meaning every two vertices of delta is connected by a sequence of one phases. Yeah? So for example, this is a disconnected disconnected. Yeah, the a complex with two facets like this. So I will usually write only the facets, so the maximal phase of the simply so complex. Yeah? So simply so complex with these facets is disconnected, while this one, for example, is connected. Yeah? Okay, so I have some notation. So, assuming that you have an idea J in a polynomial ring S, I use another ring different other than R, and let N be the this notation for the greatest maximum idea of S. Yeah, so it is generated by y1 up to ye. Then by definition, this is the saturation of J. Yeah, so the union of column of J2 powers of the maximum greatest maximum idea. And why is this guy relevant? Because if you compute the zero hollow homology, yeah, so by definition, this is everything in S mod J, which is kin by some power of N. Yeah? And so if you compute it, then it is actually this constant, yeah, saturation of J over J. And so this is, you see, this is relevant to our discussion of depth. So when depth of this guy is, so depth 0 will mean that it is different from saturation is very different from that.
What do you mean by H0n? You mean cohomology or something?
Local
H
homology. Yes. So it is just this you can define directly. Yeah. So everything in as most say that it is kin by some power n. It is the zero local homology. Of as most say we support n. So okay, so you can prove the following. Now F is a subset of D. This is a criterion for when delta the degree complex of when the
so
degree
the
complex.
so the depth is 0 if and only if the saturation of the ideal will J will become a saturated ideal, right? You write inequality there.
Different. Depth 0 meaning the saturation is different from J. So depth 0 meaning that the zero local homology is non-zero.
Sorry, say it again.
So that equal to 0 mean here recall that is the minimal point where you have non-zero local homology. Yeah? So that 0 meaning that's a zero
Okay,
local
okay, okay.
homology.
No, okay. We are interested in non-zero. Okay, 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 okay. Now I okay. Thank you.
So you're welcome. So this is a set, and we're looking at the polynomial ring with variable not in F. Yeah? And we look at the localization of I at F and pull back to S. Yeah. So this is a monomial idea in S, and you obtain by replacing all the variable in F by one. Yeah. Then from I you get another monomial idea J like this. And now let A in Z to the D be any vector such that the negative support of it is exactly F. And I also denote by A plus the vector with the components like this. So max of A1 0 to max of AD 0. Yeah? So if a component of A is negative, then you replace it simply by 0. And if that component is positive, then you fix it. Yeah. So this is a vector in n to the d, yeah? And it's a set of non-negative integers. So we have this criterion. Yeah? So delta I of I is this complex if and only if x A plus is belong to the saturation of J minus J. So from this, in particular, we have depth of S most J is positive if and only if for all A in Z to the D such that the negative support is F. We have that degree complex A is different from this complex. Okay, so using this, you can this takes some time to write out, but the proof is not difficult, and so I will just mention some consequences of this. So as the so for example, a consequence of this is the following. Is a condition for the vanishing of the first local cohomology. Yeah? So the following are equivalent. We are interested in depth at least 2. Yeah, depth at least 2. So we are, if depth is at least 2, then the first local cohomology will be 0, right? So that's why we are interested in this condition. And this is equivalent to the following condition. Yeah. So maybe here I write a notation here. This is the Rj, yeah, where J is from 1 to D. It is a polynomial ring in variable different from Xj. Yeah? And Ij, it's simply I you localize at Xj. Yeah? And then you intersect back to this smaller polynomial ring. Yeah? So in other words, Ij is the idea you obtain from I by replacing Xj by 1. Yeah? Then you get Ij. Then this is equivalent to the following. The first local cohomology is 0 if and only if for every J from 1 to D. The Ij has positive depth. And for all vector with non-negative components, the degree complex is connected.
can you shed light on this IJ more? How what was the purpose of how it differed from the
Uh,
okay,
so
yeah,
yes, so
yeah.
as I said, IJ is the idea you get by so assuming that your I is generated by the generator M1 up to MQ, for example, and then IJ is the idea you get by mapping HMI to MI prime, yeah, where you the rule is to replace XI if any, yeah, if some power of XI uh, is there in MI, then you replace J by 1. Yeah.
One.
So, for example, if you have this idea from the last time, right? Then I1 would be the idea you get by replacing X by 1. Yeah. So it is this the whole ring, right? I2 is the idea you get by replacing Y by 1. Yeah. So you see XQ Z times D. Yeah, and so on. Yeah.
Now, when we take the intersection with
Yes.
IRXJ. Oh, so this is the direct way of computing IJ, right?
Yes.
Ah,
Here
okay.
it is the same as first. This you can think of as the idea obtained by inverting xj. Yeah.
Mhm.
Yeah. But then you stay in the polynomial ring. You don't stay in the localized polynomial ring, but you just stay in the polynomial ring,
Okay.
smaller polynomial ring. Yeah. And you get this
This
monomial.
this example helps. Thank you.
Yes. You're welcome. Okay. So so to prove this proposition, you only need to uh, to dig in the local cohomology. So, for example, why do you have this condition? Yeah, because if you have that this is equal to 0, right? Then for every A in ND, so I do not give a proof for this, but I explain you roughly the proof, the easy proof. Yeah. Then of course you should have that it is 0 in this degree. Yeah. But by Takayama, yeah. Now A has no negative support, so this is 1 minus 0 minus 1, right? Because G of A is empty set, delta AI A, right? So that is H tilde of 0 of delta AK. So this is 0, meaning that delta A is connected, right? So that's why you have this condition here. And for this condition, the reason is, for example, you take A in Z to the D such that this A above, we have A with no negative component, right? Now we look at A with one negative component. Let's say G of A equal to Z, yeah? So then what happens? So you also have this vanishing in A. Now GA has one component, so it is 1 minus 1 minus 1, right? So this is S tilde minus 1 of delta A I of K. And we said about what it means to S minus 1 to vanish, right? S minus 1 is vanish if and only if. So this is if and only if delta A of I is different from this complex with only the empty phase. Yeah. Okay, so we want to have that for every A in DD such that the negative support is they we have delta A I is not the empty complex like this. And so from this very lemma, yeah, this very lemma with f equal to j, yeah, f equal to this 1 point set, then you see that it is exactly s here is exactly rj, yeah. This s, if f is j, then s here is exactly rj, and this j here is exactly I localized at j. Yeah. So that lemma tells you that this is if you want this for every A, yeah, with negative support being j, then it is equivalent to that of rj modulo ij is positive. Yeah. So and and the other vector you might have is that the vector with at least 2 negative components. Yeah, but it is easy. Yeah? In this case, you can check that again by Takayama 1 minus GA minus 1 delta A and but this is smaller or equal to minus 2, so this is always 0 for every complex, right? So that's why in this condition you only need these 2 conditions. Yeah? So okay, so finally I can state the condition for depth at least 2 for unmixed monomial ID. Yeah? And then the following are equivalent. So the depth of R mod I is at least 2. It is equivalent to first depth of R mod I is positive, and so this we know that you can check by looking at the associated prime, right? The maximum idea should not belong to the associated prime. So secondly, all the localization of I at one vertex has positive depth. So Rj and Ij is as in the previous result. And finally, for all non-negative vector in R n to the d, this degree complex is connected. Okay. And this is very easy because, so for example, if you have these 3 conditions, then the first condition tells you that the zero local cohomology of R mod I is 0. Yeah? And these 2 conditions tell you that the first local cohomology of R mod I is 0. And so the depth must be at least 2, right? Because it's the first non-vanishing of the local cohomology is 2, yeah? not 0 or 1.
Hope, but what is the role of unmixedness here? So basically, this result is derived from the Takayama. and the above
Yeah.
explanation. So what is the role of unmixedness?
Actually, you don't need unmix here. Yeah, I just, if you want, you can erase it. Yeah? In this result, I don't really need unmix.
Apart from this result, uh, does unmixedness imply something in this particular construction of the depth computing? Most of the cases in all your explanation.
Yes, so this there's a result that I need unmixed, but I will state it now. Yeah. So here is a result that I will need unmixed. So in this result, we can completely describe the facet of the degree complex, yeah, for every vector. This is a vector, yeah. Then okay, the facet. This is the notation for the facet. The facet of the degree complex is every set of this type where f is a facet of delta I we know, yeah. F containing G8 and such that x to the a plus does not belong to IF. Okay, so I should explain this. So you know, if f uh, if f is a phase, is a facet of delta of I, then this is equivalent to if we take all the variables not in F, yeah, this I denote by PF. This is an associated prime of I, and so IF will be the IF in the end it is I localized at F and pull back to R, and this is exactly the, but it is somehow easier to compute than this localization because it is exactly the primary component associated to PF. In the primary decomposition of I, yeah. So so this is how you can find all the facet of delta A, yeah. So maybe it is easier to, yeah.
IF is the primary component of PF is a primary component of IF. You mean?
PF is an associated prime.
Associated prime of I, and then IF is a primary component of PF. You mean? What do you mean by that?
No, primary component of I. Yeah.
Okay. Now it's
So you know this is an associated prime of I, yeah, and I is unmixed, so it has a unique primary component whose radical is PF, and that's primary component. I call it IF.
interesting. Thank you.
So this implies the following. So again, I is unmixed, yeah. A now is just a non-negative vector. So in this case, the negative support of A is empty, and so you see that the facet of delta A of I is exactly the facet of delta I. And okay, A plus, A is non-negative vector, so A plus equal to A. So you see here you have only the condition that X of A does not belong to the primary component of I corresponding to F, yeah, or corresponding to P of F. Maybe I give an example here for this formula. So we take this monomial idea. So you can ask, for example, this is a question that we interested in last time. When is this local homology non-zero, right? Okay, in this case, yeah, A is now a non-negative vector in R form. Yeah. So if you use this formula, then you see that okay, first we need to compute this complex, and it is obtained from this radical of I, right? It has this primary decomposition, and so you see that's the facet of delta I. So this one you have the facet ZT. Yeah? This one give you the facet, so you take the complement, then you get the facet YT. And finally, the last one give you the facet YZ. Yeah. So yes, so this formula, for example, tell you that the facet of delta A of I is everything belong to this. Yeah? F is in this set such that X to the A does not belong to IF. Yeah? So you can take some vector, for example, A is equal to I don't know, 2011, for example. Yeah. And then you can easily compute this, right? Because yeah. So for you can compute, for example, I of this. What is I of this, right? The primary component of F, for F equal to ZT. Yeah, the primary component of this guy is e to the cube Y, right? Because you have this primary decomposition for I. So this is
I mean
the
the primary
component
component in the original idea, not in the radical, right?
Yeah, in the original idea. Yeah, and this is a primary component in the original idea I. Yeah, and similarly, I of YT is EQC, and I of YG is EQT. Right? So given a vector like this, you can easily compute. Yeah, for example, X to the A in this case is X squared ZT, right? So you see X squared ZT does not belong to I of VT, right? Which is X cubed of I. So this tells you, for example, that this is a facet of delta of I, yeah, of delta A of I. And similarly, you see that this belongs to this, so it tells you that this is not a facet, yeah, YT and also YZ. These are both not facets of delta A of I. And so we see that in this case, the facet of delta A of I, you easily get that it is only this ZT. Yeah. So with this formula in this corollary, you can easily compute the facet of these complexes. Yeah. For non-negative vector and for arbitrary vector, you can use this formula here. So the difference here is that the IF here are a monomial idea, right? While the IRF here are not monomial idea. Yeah? Is idea in some localized ring. Yeah?
Again, the question is the same regarding to what is the role of unmixedness. Okay, in the computing example, it seems to be that can be true for any case. Probably I'm thinking a little bit more louder on it.
Yeah, actually, I don't have a time to present the proof here, but in the proof of this proposition, at one point you need unmixed. Yeah. But
yeah, in the computing, in the example of the computing example, seemingly that, yeah, probably the example is showing that it can be done for any case.
Yes, so the moral of everything here is that you can do everything for mixed monomial idea. Yeah, but you know, the most interesting ideas are prime idea and radical idea and primary idea, and those are unmixed. So of course, you want example unmixed example because that's a nice idea.
Yeah, definitely. The structure is nice with when it is mixed. I would like to see the. Is there probably is there any counterexample where we relax the condition of mixedness, and there does not exist such a case? That would be an interesting case to look at. Any counterexample? I'm sorry. Probably this is too quick to produce any. Disconnect हो गया? Disconnect हो गई? Disconnect हो गई? हैं? Disconnect हो गई? Pause करते ना recording.
Sorry, I was disconnected.
Yeah. I hope probably you would like to conclude the things now.
Yes.
Yeah.
Sorry. I will try to finish in 5 minutes. Yeah.
Anyways, this happens. We understand.
Okay. So I share my screen again. So we have what we did was this. So we give a criterion for combinatorial criterion for lab at least 2. Yeah. So the point of this result is that the one and the first and the second condition you can take easily from the primary decomposition of the idea I. You can read easily whether the depth is positive or not. And the third condition, the connectedness of this degree complex, yeah, you more or less can also can do by combinatorics because you know what are the facets of delta A of I. Yeah? From this, you know completely the facet of delta A of I, so you can tell when it is connected or not. Right? And so using that, we have this theorem that give a class of symbolic depth function with values only 1 or 2. Yeah. So now I work only with polynomial ring in 5 variables. And I let M, P, Q be primary monomial idea. Such that radical of M is x, y, z, radical of P is x, y, and radical of z of Q is z. Yeah, and then I look at this unmixed monomial idea. M intersect with GU intersect with QV. Yeah, Q plus this means P plus U, and this means Q plus V. So then the symbolic depth of I is only 1 or 2. Yeah? And secondly, the symbolic depth of the T symbolic power is 2. If and only if you have this relation between M, P, and Q. Yeah. So you only need to check this condition, and then you know whether that is 1 or 2. Yeah. And in particular, so this gives you the following example. That for you choose M to be x squared, y squared, z squared power 2, P to be x cubed, y cubed, and Q to be z. Yeah, and then you take I as above and intersect with PU, intersect with QV. Then you have a clearly a periodic depth function with a period 2. This will be 1 if n is odd, and 2 if n is even. So so that's it. So that means that the symbolic depth function of I is really periodic, right? Generally periodic. Yes. So finally, just a comment about this theorem. Yes. So to prove this theorem, part one is very easy. You know the primary decomposition of I, so you know the primary decomposition of the symbolic power of I. Right? And so from this decomposition, you also know that the symbolic power has dimension 2. So the depth cannot be bigger than 2, and the depth is positive because M is not in the associated prime, right? So this first one is easy, and the second one you use the above criterion for monomial idea with depth at least 2. And in fact, for IT, for our idea IT, you can check easily that the first 2 conditions are satisfied trivially. So the only relevant condition is the third condition on the connectedness of the degree complex, and that you can translate to this condition. Because in this case, you know also precisely what are the facets of this complex. Yeah, it has only 3 facets. Yeah, so it is very easy to discuss when is the degree complex of delta. The symbolic curve with respect to some vector is connected or not. Yeah. Okay, so yes, so I guess it is the end of my lecture today. Thank you very much.
Thank you very much for your lectures. And this final theorem by whom?
Yes, so this is due to me and Nguyen too. And it was published in 2019. Also, this example.
Mhm. Yeah. And
Actually, yeah, sorry. Actually,
yeah, yeah,
I
please
was saying
continue.
we first discussed is when I more or less right before the first time I go to Lahore, I went to Lahore. Yes, so in
That's fine.
2018, and this.
And
Yeah,
what are the potential questions in this direction now?
yes. So I was also preparing for that, and there are many other questions that you can consider. For example, a very interesting question is about regularity, and so the question is whether the regularity of the symbolic power is always linearly bounded. Yeah. So almost nothing is known on this question. The case of monomial idea, unfortunately, is easy. Yeah? But for non-monomial idea, we don't even have about all for the regularity of the symbolic powers. More relate, more relevant to that is the question whether this function can be not eventually periodic. This I think is also very interesting. We do not have any example, and the problem is that our techniques here are only for monomial ideas. And for this, you have to work with non-monomial ideas. And yes, we do not have too many techniques to do that. So there are many other questions on symbolic powers. People are still looking at these questions.
Thank you very much for wonderful series of lectures on very interesting results. And definitely, Professor Chung is the king of this theory somehow, symbolic powers, and when it comes to the regularity and depth computing. And these results are very interesting. And thank you very much for your elaborations. I'm sorry, I time to time I poke you many times in your lecture, but
No, it's
literally
okay.
speaking, every time you come up with a very clear explanation on the things. That's really remarkable. And we wish to have you here, but maybe in near future.
Yeah,
Thank you. Hope.
yeah, I hope we can meet in person soon. Yes.
And
Sorry about the
I request.
interruption.
I request all the participants to applaud for Professor.
Thank you
Definitely, it
very
is
much.
really hard to be as expressive as possible through online, and you did a remarkable job. I really appreciate. Thank you from all the participants, and we wish you. Okay, I will wish that Vietnam will revive the situation of the COVID. Vietnam will recover from the present situation very soon.
Yes, thank you very much.
Thank you. Now we have with us